Oh, it's okay now.
Okay, good.
We first start with the background, such as state protection, decoherence, and control. Then we review two kinds of main quantum control schemes, that is quantum feedback control and quantum feed-forward control. Then we introduce the quantum composite control. And finally, we'll discuss the experimental feasibility of quantum composite control. Noise is everywhere, and this makes state protection important in practical quantum computing and quantum communication. The state protection task aims at making the output state be as close as possible to the input one in the existence of noise. And there are several methods to achieve state protection. For example, quantum error correction, dynamical decoupling, decoherence-free subspaces, weak measurement-based quantum control, and etc. In this topic, we would focus on the weak measurement-based quantum control. Before beginning, let's review two typical kinds of decoherence. The first one is the dephasing noise. It can also be called as phase damping. In continuous time, the dynamic of dephasing can be defined by the Hamiltonian of this form. Here, A dagger, B dagger are annihilatory and creation operators. In discrete time, dephasing can be re-expressed by operation sum representation by the following two cross operators, E0 and E1. This means that dephasing will give a sigma Z error with probability R and no error with probability 1 minus R. The output of any input state row after noise would become this form. Another typical kind of decoherence is the amplitude damping noise. The Hamiltonian has this form, and the operation sum representation has cross operators as these two. They are different from the dephasing one. Next, we record the weak measurement-based quantum control. An example of weak measurement mainly used in quantum control schemes has the following form, which has two measurement elements, M1 and M2. Both of them are encoded in a diagonal basis with strings P. And then the state after measurement will become this form and with a probability of this. Notice that when the strings P is ranging from 0 to 1 and not being 0 and 1, the measurement is non-projective and be weak. When the P is equals to 0 or 1, the measurement becomes projective and thus strong. Why should we use weak measurement in measurement-based quantum control scheme? That is because weak measurement can achieve a balance between information gain and back action, which are two difficulties in design quantum control scheme. The information gain means the information acquired about the measured system. However, the measures generally will disturb the measured system and drive the system to an unexpected state. And that is what we call back action. There is always a dilemma between information gain and back action in a measurement-based control scheme. And studies have shown that weak measurement can solve the problem. A weak measurement-based quantum control scheme basically have two kind of operations. The first is weak measurement M, and then the measurement outcome MI would provide information for further correction. such as UI. Let's review two kinds of weak measurement based quantum control. The first one is quantum feedback control, and QFBC for short. The theory is presented in a discrete time and a single qubit system in 2006 and 7, and then the experiment is implemented in 2010. This control is quite easy and clean, and it just applied a control after noise, and no measurement results would be abandoned. That means the control would succeed with unit probability. And quantum feed-forward control is quite different. It applies a control before noise and a reversion after noise to recover the system. The reversion includes a reversed unitary and a post-selected measurement, an M. Notice that there are measurement results are being abandoned, and so the success probability may not be unit. And there is another explanation of the reversion, that is the pre-weak measurement element, an M, and times the post-selected measure. An M is supposed to be approximate to identity. And quantum feed-forward control have a special advantage that it can protect an unknown state, a totally unknown state, which quantum feedback control cannot achieve it. And naturally, one may think that whether we combine quantum feedback control and quantum feed-forward control would improve the protection. And our answer is yes, and it would not improve protection trivially. Before introducing the composite control scheme, let's first state the problem mathematically. Suppose Alice tries to send a qubit to Bob through a noise channel, which is prepared in random of two non-zero states, psi plus and minus. There are two unknown variables, theta and phi. And suppose the noise, the decoherence noise is amplitude damping, and it would have these two cross operators. Then the goal for Alice and Bob is try to control and protect the qubit without knowing which state the qubit is in. The schematic diagram of quantum composite control is plotted as at the left hand. Firstly, Alice would make a pre-weak measurement, which has two measurement elements, M1 and M2. Then she would apply a feed-forward operation based on the pre-weak measurement outcome. That is to say that if she got a result M1, then she would apply the unitary identity, and otherwise she would apply a poly X. Then after that, Alice will send the qubit to Bob through the noisy channel. Then Bob receive the qubit, and he would apply a reversed operation UI based on the pre-week measurement outcome. After that, Bob would take a post-week measurement based on the pre-week measurement outcome. That is to say, if Alice get a M1, then Bob would apply a measure that consists of elements N1 and N1 bar. If Alice gets a M2, then Bob applies another measure which consists N2 and N2 bar. After that, Bob would do the abandon action or feedback rotation based on the post-week measurement results. The feedback rotation is a rotation about the y-axis with opposite angle based on different measurement result. And that is the composite control. Then we would make a comparison between composite control and other control schemes. We first start with the framework. They are quite different. A review that quantum feedback control did control after noise, and quantum feed-forward control did control before noise and reversion after noise. And our control combines quantum feedback control and quantum feed-forward control in a non-trivial way. The non-trivial is lines in that the post-week measurement result in the reversion of the quantum feed-forward process is treated as the weak measurement of the feedback control process. You can see the third process chart, and in order to distinguish the non-trivial and the trivial combination, we also consider a trivial combination scheme, which is short for TCC. And there, quantum feedback control and quantum feed-forward control are applied one by one. And there is then we would refer to the performance. The first comparison is about the fidelity. This is an important measure of quantum control. And please see the figure. That is a fidelity and the fidelity improvement figure. The upper three figures are fidelity improvement of quantum control schemes over other schemes, and the subfigures under at the bottom are the fidelity of quantum composite control, and they are in pairs. For example, A and D are pairs for different phi, for phi equals to 0, and so far others. And we can see that there is a apparent improvement, and the maximum improvement is 0.08. That is, you can find from the subfigure C. And especially when the phi equals to 0, you can check the subfigure D, and the fidelity of quantum composite control would be generally high, and it would do less than 0.93. And another important measure is success probability. We already know that quantum feedback control has unit success probability. Quantum feed-forward control have non-unit success probability, and so for quantum composite control, you can see from the figure, the red curve represents composite control. And this is a figure of fidelity success probability plot. And the red curve can be very close to fidelity 1 if we ignoring the success probability. And for each fidelity point, the red curve is always at the top of other curves, and that means the success probability of composite control is always greater than others. And the table listed selected fidelity and corresponding success probability. For example, when requiring the fidelity to be 0.8573, the success probability of composite control would be unit. However, others would not achieve unit, and we find the success probability improves 0.677 over the triple combined one, and 0.744 over the quantum feedback control one. And actually, quantum feedback control cannot achieve this fidelity in this case. The physics behind the composite control is actually not complicated. We give an example to show the physics behind. We choose the input state to be the following form. In the Bloch sphere, these two states would distribute at both sides of the axis with the same angle theta. And we find that after the quantum feedback process, and if the post-weak measurement get a result N1, then the state will evolve as a mixture of the initial state itself and the state 0, and then feedback rotation Ry alpha would correct the 0 error. This is why the composite control improves the protection. The difficulties in experimentally implement the composite control lies in the operations used in composite control scheme. There are three kinds of operations: a weak measurement before noise, a weak measurement after noise, and a unitary rotation after a measurement. The first and third operations have been realized in a photonic setup in 2010, and the second operation has been realized in 2012. And to sum up, it's not hard to find that the composite control is totally realizable with current techniques. This is all my speech. Thank you for your attention, and questions are welcome.
Okay, thanks. Yeah, so we actually got 2 questions from the audience. So the first one is, does weak measurement-based quantum control outperform other methods? How do other methods like quantum error correction perform on the state protection task?
So there are differences between quantum error correction and weak measurement-based quantum control. So they use different resources, such as quantum error correction would use entanglement to correct error, and they do not need to know the information about the initial state. But weak measurement quantum control does not need to use entanglement, and it just need weak measurement and operations. That is say that I think the weak measurement best control is cheap, but the error correction would have better protection, I think. They are different.
Okay. And the second question is, what does fidelity mean? How does it verify better performance of QCC?
Sorry? Pardon?
So what does fidelity mean? How does it verify the better performance of QCC?
Okay, the fidelity is we have the input and the output. So compare the input and the output state. We got a fidelity that is the similarity between the input and output. So we know whether the output state is how close is the output state to the input one.
Okay. So let's thank CaoYa. So I think the whole session of this talk session in female forum has already finished, and I think in 10 minutes the panel section gonna start. Okay.
Thank you, and looking forward to panel.
Okay.